Hi guys, and welcome back. I wanted to put together a video for my calculus class, section 3.2, where we talked about two main theorems, Rolle's theorem and the mean value theorem. So starting off here, we got the definition here for Rolle's theorem. Rolle's theorem is an existence theorem where we have a continuous function and differentiable function, and at some point between the interval that's given, we are going to have a max or a min, or a critical value. Okay, so by definition here, it says let f be continuous on a closed interval from a to b and differentiable on an open interval from a to b. If the endpoints are the same, f of a equals f of b, and again here this is your a and this is your b. If the endpoints are the same, then there's got to be one value in between them where your derivative or your slope is set equal to 0. So I've got an example right here. We've got f of x is 1/2 x squared minus 6x going from 0 to 2. I got the graph right here. As you can see, we got a parabola. Well, first and foremost, that's continuous. That's what we got to have first. The second part that we got to have is, all right, we're differentiable. So let me check right here. If I find the derivative, I shouldn't have any problems with the derivative, which will wind up being x minus 6. So there's no problems with the derivative. You would run into problems if you had like a rational function that wound up being your derivative and you have zeros at the bottom of that, but we don't have a rational function, so we're good. So the second part is being differentiable, so we're good with that. After that, we've got to check that the endpoints are the same, and you plug a and b into the original function. So if you plug in f of 0, you wind up getting 0, because 0 squared and all that, minus 6 times 0. And then what about f of 12? Well, let's see if we can figure that out. That'd be half of 144 minus 6 times 12. So half of 144, that's 72, minus 72. Yeah, we get 0 again. So we got 0 for both of these. So that's the third condition that we got to have right here, is that the endpoints are the same. If all three conditions are met, and we can see right here, if we're going from 0 to 12, so I can pretty much bank on looking at the graph here. Here's 0, and here's 12, because we were getting 0 for both of those. At some point between these two numbers, we are going to have a slope or horizontal tangent line where the slope is 0. Now you can see right here visually that right here we're going to have a horizontal tangent line at the minimum of that parabola. So the way we find that is after three things of being continuous, differentiable, and the endpoints, what you do now is you just find the critical value. And again, we find critical values by taking the derivative, which was x minus 6, and setting that equal to 0 and solving for x. So pretty easy right here. We just move the 6 over. And we know that at x equals 6, that is where we're going to have a max or a min occur between 0 and 12, which makes sense because x equals 6 is right about there. Okay, so that is Rolle's theorem. Let's try another one here where we're doing that. So I've got this one. We've got x to the 4th minus 2x squared, and we're going again from negative 2 to 2. So there's your a and there's your b. So from negative 2 to 2, so there's negative 2 and there's positive 2. So between those 2 points, as long as we're continuous, well, as you can see, between those 2 points we're continuous, no sharp points, nice smooth curve, and we're differentiable. So let's make sure we find the derivative. So the derivative is going to be what? 4x cubed minus 4x. So there's no problems with the derivative. And then the endpoints have to be the same as well. So if we check the endpoints, okay, so that means I've got to plug into the original function, f of negative 2. So that's going to be what? Negative 2 to the 4th, that's 16, minus 2 times 2 squared. Yeah, that's going to be 4. So we're going to wind up with, what, 16, that's going to be 8. And then if I do the same thing here, f of 2, I'll wind up with 16 minus 2 times 4 again. We're going to wind up with 8. So the endpoints are going to be the same here. All right, so at negative 2, actually, I got a little off right here, that I'm not actually right here at negative 2 and positive 2. I am at the y value of 8. So I don't want to use these two because that's not exactly where that's at. I'm actually going to be at 8 and negative 8. So I could barely see right here. That's 0. There's 1. There's 2. So actually I'm looking at a window pretty much between here and here. So between those two values, okay, I got to make sure I'm continuous, no problem, and I'm differentiable, which was no problem. So that means I got to find the critical values. Now you can actually see right here again, where do I have mins and maxes between negative 2 and 2? I got one right there, I got one right there, and I got one right there. So I take the derivative, 4x cubed minus 4x, and I set that equal to 0. So I got to solve for x. So I can actually factor out a 4x. And I'll have x squared minus 1. And then I'll have 4x, and then that's a difference of squares, x plus 1, x minus 1. So my critical values, I'll have 3 of them. So I'll have a critical value at x equals 0. There's 0 right there. I'm going to have one at negative 1. And look at that. There's x equals negative 1 right there. And positive 1. And there's my other one at positive 1. So it helps looking at the graph, obviously, to see that. So there's actually 3 places applying Rolle's theorem that if I'm on a closed interval here that's continuous, differentiable, and the endpoints are the same, then I will have some critical values here, or some maxes or mins that will occur. Okay, so hopefully that helps clear that up there for Rolle's theorem. Okay, I also wanted to talk now, if I go over here, I want to talk about the mean value theorem. Now the mean value theorem is kind of similar, but if you notice here, we're not taking the derivative and setting it equal to 0. We're actually setting it equal to a number. This is a number right here that we're going to figure out. And the mean value theorem, if you remember from Algebra 1, this word right here, that means average. So we're taking the derivative, okay? Now derivative means slope. So we're taking the actual slope and setting it equal to the average slope. Now visually, on a graph, graphically what that means is pretty much this. If I've got a curve going from A to B, and I got a curve that kind of looks like this, okay? At some point between them, if I take the slope of the 2 points, that's your secant line. That's your second part right there, okay? At some point in between them, I'm going to have a point that winds up being in between where my slopes will be parallel, where my slopes right here will be the same. So we're trying to find where we're going to have the point at which the slope of the tangent line is the same as the slope of the secant line. So the first part is very similar to Rolle's theorem. You got to make sure that the function is continuous and it's differentiable. And then once that happens, you take the derivative and you set it equal to a number and solve for x. Okay, so you're not finding a critical value, you're just setting it equal to a number. Okay, so let's take a look at this first one here. We got f of x is 3x squared plus 5x minus 2. Now that's a parabola. I don't have the graph up here, but I know it's a quadratic, so it's got to be a parabola. That's continuous. Okay, so second thing I got to do here then is find the derivative. Okay, that should be no problem. We've had a lot of practice with derivatives. 6x plus 5. No problems with the derivative because it's not a rational derivative. We wind up with being okay from negative 1 to 1. And now what you have to do is you have to figure out this second part here, because we're going to take the derivative and set it equal to a number. So again, remembering here that your interval goes from a to b, and you have to figure out then what f of 1 minus f of negative 1 all over 1 minus a negative 1. That's what this whole thing is right here. Okay, that's that formula. So again, this goes in the original function. So f of 1, all right, so if I plug this in here, I'm going to wind up with 3, 1 squared. So that's 3 plus 5, that's 8, minus 2, so that winds up being 6. And then plug in negative 1. So again, that's going to be 3, and then that's going to be minus 5, and then minus 2. So that's going to be a negative 4, so that's going to be a plus 4 there, because back-to-back negatives. And then 1 minus a negative 1, because it's just b minus a on the bottom there, so that's going to be 2. So that gives us 10 over 2, which is 5. Now, that 5 is what I'm going to set the derivative equal to. So I got to take 6x plus 5 and set that equal to 5. Solve for x. So subtract 5, you'll get 6x equals 0. Therefore, at x equals 0, between negative 1 and 1, at x equals 0, the slope of the tangent line and the slope of the secant line are parallel. They're the same at this point. Let's try one more. Okay, I want to apply the mean value theorem. Okay, so again, the mean value theorem is where we're taking the derivative and setting it equal to a number. Okay, so the first things first, let's find the derivative. Well, the derivative of a constant, 0. And then right here, we've got negative 4 over x. Actually, I want to change that here for a second. We don't want x. We don't want x squared. We just want x. So let me erase that here real quick. We're just going to do 4 over x. Okay. So if I'm taking the derivative right here of just 4 over x, I'm going to have just some side work here. That's negative 4x to the negative 1. That'll help me do the power rule for the derivative. So I'll have 4x subtract power by 1. So that'll give me 4 over x squared. Now, we do have a rational function. What makes the bottom 0 here? Well, 0 do, right? There's a discontinuity here at 0. But if we notice, our interval goes from 1 to 4. And 0 is not on it. So we're actually okay continuity-wise and differentiability-wise, because 0 is outside of the interval. So if we're just looking from 1 to 4, we are continuous. If we're just looking from 1 to 4, we are differentiable. So we're okay with that. So my derivative winds up just being 4 over x squared. Now, I got to figure out the second part here. I got to figure out what f of 4 minus f of 1 all over 4 minus 1 is. Okay, so plugging in 4 to the original, I get 5 minus 4 over 4. That's 5 minus 1. That winds up being 4. Plug in 1. 4 over 1 is 4. 5 minus 4, I get 1. And I got lucky here. They're actually the same thing. So I get 1 for the number. So again, what do we do with that number? We take that number that we got right here, okay, and we set that equal to the derivative. And that our derivative, again, that was the derivative we got here, so which was 4 over x squared is equal to 1. Now, to solve this algebraically, I'll just cross multiply. You got x squared is equal to 4. And we will see here that when we take the square root, x is equal to plus and minus 2. Got to be careful here. This is where the slope of the tangent line and the slope of the secant line are the same, but we're only looking between 1 and 4. So since we're only looking between 1 and 4, we can cross out the negative 2 and only use x equals 2 for our answer. So hopefully that will help you as a review for the mean value theorem and Rolle's theorem, and while you're doing your homework and reviewing for our test. Thanks for stopping by, guys.